This is potentially one of the most confusing setups to a topic. Um, when I ask grade 12s, how did it go, like that sort of thing, whether online or in person, nobody really likes the setup to this topic. So I've reworked it, I've added videos, I'm adding this little video of me yabbering through it. But the feedback is the setup of it is confusing, but once you get through the setup and start working through the questions, then it kind of clicks. So I'm gonna hopefully you watch this video. This is going to be me talking you through the content, talking you through all this stuff that I've typed. And hopefully that helps the going through this make a little bit more sense. But even if you get to the end of this and you're still a little bit confused, taking the time to watch me solve questions in those other videos, to try questions on your own, that's where it's really going to click. So I'm asking you to be patient, give this a whirl. And if you're rattled at the end still, don't freak out. You can email me or try some of the questions and see if that clears it up. And if you're still rattled, shoot me an email, talk to each other. But I think we'll get through this together. Just know going in that this is a topic that tends to bug people as we set it up. All right, first off, if you haven't yet, I'm not going to pause the video quite yet, but right at the very beginning of this note, I've got some video clips of things going through what I'm calling harmonic motion. So instead of me making two video clips, if you haven't yet, pause this video and open up those ones that I've highlighted and take a look at what harmonic motion looks like, and then rejoin this and I'll talk you through what it is. All right, so I'm trusting that you've watched those 4 video clips. The topic of the day, the topic of this lesson is something called simple harmonic motion. Harmonic motion is the motion to describe something that's vibrating. So if anything, this topic is an extension of what we learned in grade 11, waves and sound. In grade 11, what hopefully we talked about, what hopefully you remember, is if an object is described as elastic, elastic means it tends to snap back to its original shape. If an object is elastic, anything that's elastic can vibrate. And when something is vibrating, the fancy physics word for vibrating is that it's going through harmonic motion. There are lots of things that can vibrate. If you watch those video clips, a wine glass can vibrate. A ruler held off the edge of a countertop can vibrate. Technically, putting the mass on the end of a string, or what we would call a pendulum, that's vibrating. All it takes for an object to vibrate, or to do this harmonic motion stuff, is the object has to be elastic, which means it has to have a restoring force. That's kind of what a restoring force is. Restoring force and elastic kind of go together. If an object's elastic, that means it wants to snap back to its original shape. And really that's what a restoring force is, that force that's trying to pull it back to its regular shape. So the bottom line is, sorry, not the bottom line, but the next line is the wine glass, the ruler, the pendulum, all of those things go through harmonic motion. All of those things can vibrate. And as you're going to see, the math behind things that vibrate, trying to describe that weird motion, that wobbling back and forth, trying to come up with an equation for that motion, it's going to be a little bit complicated. We got an object swinging. We're going to use the word amplitude from one amplitude position all the way to the other amplitude position, then back to the first amplitude position over and over again. As it wobbles back and forth through those range of positions, the velocity is changing constantly, speeding up and slowing down, then speeding up and slowing down, changing direction, speeding up, slowing down, like back and forth, fast, slow. And we don't do a lot on acceleration this year. You might see it again where you head next, but the acceleration is changing over and over again. So harmonic motion is complicated, as we often do when learning physics. We're going to start with a special case, a simpler case, and then build on it. So in high school, we're going to start with a simple case called simple harmonic motion. Depending where you head after high school, and maybe your next physics course, you'll bump it up and talk about just regular harmonic motion or a different version of harmonic motion. A neat connection to harmonic motion, it actually shows up in quantum when you start studying the model of the atom. So depending where you go in chemistry or some higher physics, you may see this harmonic motion stuff again in quantum. Anyway, for now, for grade 12 physics, we're going to start with this topic called simple harmonic motion, or SHM for short. the definition of simple harmonic motion is, well, any harmonic motion has to have a restoring force. If we look at the restoring force and we do some math on it, and when we do the math or we do like a free body diagram and look at it, if it turns out that that force is proportional to the distortion, then we say that that harmonic motion fits, and we'll call it simple harmonic motion. If we write it out in math, if we do like a free body diagram and when we're done looking at the force and we build an equation, if it works that the force is equal to a bunch of constants multiplied by S, or what I typed it, that means that the force is proportional to S. If it ends up that the force looks like that, then we can say that it's simple harmonic motion. If we do a little bit of work, kind of this little bit in italics down here, if we do a free body diagram and after looking at it, we get the force is a bunch of constants multiplied by S squared. That's going to be a harmonic motion. It's just not simple harmonic motion because it's got an S squared instead of just a plain old S. Or when we start looking at the pendulum does harmonic motion. When we start looking at it, we get some constants, so some letters in the brackets, and I'm going to start all over again. When we look at the pendulum, at first go looking at the pendulum, we get that the force is equal to a bunch of constants, but it's multiplied by sine of the angle. The pendulum is definitely harmonic motion, but since this is not plain old S, then that harmonic motion isn't simple harmonic motion. So to have harmonic motion, there has to be a restoring force. If when we do our forces analysis, the restoring force is a bunch of constants multiplied by S, which mathematically means force is proportional to S, then we can say that that harmonic motion fits simple harmonic motion. There's all sorts of other harmonic motions, but to be simple, the force has to be some constants multiplied by S. Again, I know this is sounding weird, but bear with me, and hopefully when we start doing questions, it'll click. So to be simple harmonic motion, oops, wrong tool. To be simple harmonic motion, we have to say that the force is proportional to S. Force proportional to S, we can rewrite that. A proportion we can rewrite, just add a constant. In a complete lack of imagination, when the people were writing this, they wrote F equals K times S. Sometimes they put X instead of S, but this is how it gets written. Force equals K times S, where K could be a single constant or a group of constants, just some things that don't change. Like maybe G, 9.8 is in there. G doesn't change, G would be a constant. Why I find that unfortunate is our condition for simple harmonic motion looks exactly like that Hooke's law stuff. Literally the lesson we did, depending on your timing, some of you did it like 10 minutes ago. It's a little bit awkward that they chose the same equation, but really what that means is that a spring, since it follows Hooke's law, and Hooke's law looks like the condition for simple harmonic motion, that if we get a mass to vibrate or oscillate or wobble back and forth because a spring is pushing on it, since a spring follows Hooke's law and Hooke's law looks like simple harmonic motion, therefore we can say that an object attached to a spring, when it vibrates, is doing this exact thing, this simple harmonic motion. In this video, this thing's very static, but if you open the document, I found an animated GIF or GIF, whatever you want to call it, and in my note, this mass is wobbling back and forth, showing harmonic motion. Sometimes there's labs about vertical springs wobbling up and down. When you did the spring lab, you had to hit stop in the animation, otherwise it would wobble up and down. That wobbling vertically on a spring is definitely some sort of harmonic motion, but because gravity is involved, it may not be simple harmonic motion. We've got two forces at play, the Ks of the spring and the mg of gravity. So we're going to leave vertical springs out of it for now. I know it's a little bit weird. I'm going to keep rolling though. The other I find very cool thing about simple harmonic motion is if we do some theoretical work and come up with some equations for one simple harmonic system. So let's say we look at that horizontal spring and we break it down and we do some cool math and we come up with equations. The equations we come up with for the horizontal spring are going to work with every other simple harmonic motion system. So if we can come up with some equations looking at a spring, we can use that spring later when we figure out if a pendulum is simple harmonic motion or not. Pendulum's a little bit weird. We'll save that till next lesson. But in a special case, we can show that the pendulum fits the condition for simple harmonic motion. But instead of a single letter in front of the S, instead of just K, it's going to have something to do with gravity, something to do with length of the pendulum. Like there's more going on in a pendulum, but it basically fits the bill that the force, the restoring force for a pendulum is a bunch of constants, a bunch of junk multiplied by S. Since these things are constants, we can take those constants and we can sub them into the equations that we come up with by looking at the spring. Just wherever we see a K from our spring equations, replace that K with this bunch of constants from the pendulum equation, and we can then apply our equations to the pendulum. I can find it's out there. I might even have it saved. I'll see if you're really curious. I can share with you. But there's a cool proof. If we took the Earth, imagine that's the Earth, and we drilled the hole right through the middle. All sorts of issues with drilling a hole through the middle of Earth. But let's say we made a tunnel all the way from here to whatever's on the other side of the Earth from us, and not to scale. Let's say you jumped into that tunnel. The way gravity works, you're going to wobble back and forth in that tunnel, kind of like the mass on the spring, except I've drawn it on a funny angle. You're going to wobble back and forth in there over and over and over again. If we do the proof on the force on you when you're some distance away from the center of the Earth, we get that it's a whole whack of constants. The mass of the Earth comes into play, the gravitational 6.67 times 10 to the negative 11 number comes into play. And if we talk about the force on you when you're some distance s from the center, it ends up that we have a linear s on the end. This is basically saying that F is proportional to S, or F equals Ks, just instead of K, we've got a whole great big ugly grouping of constants. If we took that great big ugly grouping of constants and we subbed it into our spring equations, those spring equations would apply. Again, hopefully that'll make more sense once we ramble through a little bit more. Bottom line for now is lots of things that are elastic. If they're elastic, that means they have a restoring force. That means they can vibrate or go through harmonic motion. If the restoring force fits this rather simplistic mathematical model that the restoring force is equal to a constant or some constants multiplied by S, then that harmonic motion we can call simple harmonic motion. Springs, Hooke's law, they look like that. So right off the bat, I know that something attached to a spring when it vibrates is going to be following this simple harmonic motion. Okay, a little bit of vocabulary or a little bit of math work. We're going to have some vocabulary. If we've got a mass on a spring that's wobbling back and forth, if this is the position where the mass would be just on its own, not moving, not accelerating, just when it's at rest, we're going to call that the equilibrium position. If we use our arm muscles and we pull it to the side some distance, so that's what's going down in this next diagram, when we've pulled it to the side a certain distance, if we drew the free body diagram, we've got a normal force up, we've got a gravity force down. They're going to cancel out. They don't really come into play. It's accelerating horizontally, so I only care about the horizontal force. The force, the restoring force, is the force of the spring. And as we talked about in the Hooke's law case, we know that this restoring force, or a spring force, Hooke's law, is always the spring constant multiplied by how far we've pulled it. So if we say we've moved it by some distance s, the force is going to be Ks. That little two-line bit of math shows that the restoring force matches our condition for simple harmonic motion. So if we come up with some equations, those equations are going to be simple harmonic motion equations. That's just sort of sort of like a disclaimer, like legal speak I got to put into the proof before we actually get into it. Vocabulary wise, if that middle point is the equilibrium, if we pull it out the farthest, oops, let's switch tools, the farthest it ever gets from the equilibrium, that maximum distance, it goes through a whole range of positions. Those are going to be different values for S, but the biggest value of S we're going to call the amplitude. We talked about amplitude in waves and sound. In your math class, you talked about amplitude, the size of a trig function. There's two amplitude positions, one on either side, A for amplitude. So the object, that should be more symmetrical. I didn't draw that the best. Our mass on the end of the spring is going to wobble out to one amplitude position, then go back through the equilibrium to the other amplitude position, then wobble back to the equilibrium over and over again. So there's your vibration from one amplitude through equilibrium to the other amplitude over and over and over again. That vibration is simple harmonic motion vibration because it's on a spring, and Hooke's law looks like our condition for simple harmonic motion. Now that we've got some vocabulary, we can come up with an equation. As the object wobbles back and forth, it's changing speed over and over and over again. It's fastest when it's at the equilibrium. We're going to call that its max speed, and the special notation for max speed is v with a little 0. It stops for a split second at the amplitude position, and then starts going again, fast through the equilibrium, stopping at amplitude. If we apply energy to that, the energy is cycling back and forth from spring potential when it's at an amplitude position to kinetic when it's at the equilibrium position. Spring potential energy is always 1/2 ks squared. Kinetic energy is always 1/2 mv squared. But we said amplitude got a special, that's a special position, it's got a special letter. We're going to call it A for amplitude. And similarly, maximum speed gets a special letter. We're going to call it V with a little 0, or V naught for maximum speed. The 1/2s cancel out, so instead of 1/2 ks squared, I get ka squared. And instead of 1/2 mv squared, I get m v naught squared. If I clean it up and flip-flop things around, I get this cool equation. Maximum speed equals root k over m times a, or if I type it kind of in a better equation editor, the fraction looks a little bit better, all under the square root sign. Maximum speed equals root k over m multiplied by amplitude. That's our first simple harmonic motion equation. There's a connection between the maximum speed and the amplitude. In grade 11, when we did waves and sound, we always said the amplitude of a vibration is related to the energy. Like if you hit a tuning fork really hard, it's got a bigger amplitude as it wobbles, and we hear that as louder. This is sort of the math that shows it. The connection is energy, amplitude is related to energy, so is the maximum speed. If we pull this object on the spring back really, really far, it's going to go faster when it goes whipping through the equilibrium. There's an example to try that, and that's where I'm going to pause this video. There are a whole bunch of more simple harmonic motion equations. It's a really, really cool derivation. It uses centripetal motion and uses this math thing called a projection. I'm going to pause here in this video. I want you to open up this video where I derive the other simple harmonic motion equations. This is the one we've come up with so far. The other equations that are embedded in that video are the other ones here, a time period equation, whatever this weird omega is, you're going to learn about that in the video. X stands for position. Really, I got a little bit lazy with my notation. This should probably be letter S to match your other stuff, and then an equation for speed at some particular time. So leave this video, go watch that video, and then work through these questions, and I think that's really when it's going to click. Email me if you have any questions.